A light elastic spring of natural length 50 centimeters and a modulus 20G. Okay, so let's write that down first. Natural length 50 centimeters, so that'll be 0.5, yeah, meters, and then modulus is 20G. And remember, that is G for gravity, yeah? Newton, so 20 times 9.8. Okay, so it hangs vertically with its upper end fixed and a body of mass 6 kilograms attached to its lower end. Okay, so there's the weight then, yeah? Remember, the weight then will be 6 for the mass times gravity, 6G. And it's held here and it's literally hanging down here, okay? The body initially rests in equilibrium and is then pulled down a distance of 25 centimeters and released. Okay, and then we've got to show that the ensuing motion will be simple harmonic. Okay, well, first of all, let's consider it in its sort of equilibrium position. Okay, so here, where I've got it here, is where it's at rest. Before now it gets pulled down. Okay, the 25 centimeters. Well, in equilibrium, of course, it's balanced, and the forces that are balancing you will be T and 6G, yeah? So we can say, look, in equilibrium, T will equal to 6G, yeah? Forces are balanced. Forces up equals forces down. But we also know how we can measure tension, okay, in a spring when we use Hooke's law, and we've got here the modulus of elasticity. So by Hooke's law, T is equal to lambda x over L, okay, where x is the extension. So we know T is 6G, okay. So we can sub that in. We know lambda is 20G. So we sub that in. We've got x, and we know the natural length is 0.5 meters. So from there then, think about what we can do, and the whole purpose of this start of this, we can actually work out what the extension is of the spring whilst it's in equilibrium before it's been pulled down a further, because it is going to get pulled down a further 25 centimeters, I think it said, isn't it? Yeah, but before then it's resting in equilibrium, and it is a stretch in this spring, okay, due to gravity, okay, due to that weight pulling down on it. So the spring is already stretched. So we know in equilibrium, forces up is forces down, so we know what the tension is, but we've got this formula as well by Hooke's law, so we can substitute the tension in, and from this we can work out what x is, what the extension is. So the g's cancel, okay, and then we can simply work that out. Okay, so we've got 6 then equals to 40x, so that implies then that x will equal to 6 divided by 40, okay. So we write that maybe as a decimal. Okay, so we have 0.15 meters. So there you go. The initial extension of the spring is 0.15 meters.